Okay, good morning. Let's continue with what we had left yesterday. We were looking at the frequency response of the common source amplifier, and we considered the situation first when there is no CGD. CGD is the capacitance that couples the input to the output in our topology, in this particular topology. And so we did the frequency response for that situation. That's shown in this green line, the magnitude, and the blue line downstairs, which is the phase response. Subsequently, we also looked at, if you include CGD, we looked at how one can use the Miller effect to actually compute what happens to the lowest corner frequency, correct? And the key take home was that because of the Miller effect, the lower corner frequency moves towards the lower frequency side, right? So what can you say about the bandwidth of the amplifier? It's decreasing. What is the bandwidth of the amplifier? And from here, these so many quantities that I have here, which is the bandwidth? Omega 2 minus omega 1? No.
No, sir. It is just 0 to omega 1.
Exactly, right? So you don't want you're making an amplifier. You don't want the amplifier gain to start decreasing with frequency. So before any of that happens, so the bandwidth of this amplifier is essentially 0 to omega 1. So omega 1 is your bandwidth. So in the absence of CGD, your bandwidth was omega 1 sub 0. And the moment you include CGD, the bandwidth has decreased, correct? And how much has it decreased by, very crudely? No, numeric, what's the magnitude? It's decreased by this quantity, GM by GL times CGD. So it's proportional to the gain, correct? So maybe we will just comment on that and then come back to this, right? So I'll say that as some closing remarks on frequency response. Okay. So first thing, we were, in the quiz and so forth, all of you have calculated many of the parameters of the common source amplifier, right? But we did not do any of the frequency related parameters. And in any amplifier, bandwidth is important, right? In everything, bandwidth is important, right from the kind of music we listen to the kind of internet connectivity we have. Bandwidth is important, right? So anyway, so the bandwidth of the amplifier, effectively you can only need to worry about things until that omega, right? Then after omega 1, what happens? Off, right? It falls off some range, it's falling off at 20, after that it's off at 40 and at 20. But for all practical purposes, once it starts falling off, you are not interested in going, right? So this is the bandwidth of the amplifier, correct? So what am I plotting here? I am plotting here the amplitude, right? So I hope you get what I am plotting, right? That's magnitude plot. Okay, and as I mentioned, this guy is this one is your omega 1. So there's a technology for this. Omega 1 comes from which one? It comes from P1, the pole P1. Now, is magnitude of P1 higher or lower than P2? Lower, right? So that pole is the dominant pole. P1 is called the dominant pole. Why is it called the dominant pole? It is the one which is determining the frequency response to a large extent. Okay. Now, one thing we did not put, which was we considered the amplifier without any coupling capacitors. Let us assume, I started off saying that the coupling capacitors are short circuits. Now, if you include the coupling capacitor, what you think will happen to this response? No, think carefully. What does the coupling capacitor do? What kind of coupling capacitor is it? So think what does lead? Okay, those are all important, but the most fundamental thing to do. So I am talking about that capacitor, correct? Well, this one you should be to comment on RA, RB, right? And the input we through a capacitor, right? And I said the capacitors are capacitors. We also discussed as to how we should design these capacitors. Okay, so what do these capacitors effectively do? They prevent the DC from going into the system. So, do you think this response will then get modified? So, suppose by chance your signal had a DC component, will it pass through? No. So, what should happen? Right. So, we did not consider that aspect. So, if you include the coupling capacitor, effectively you will have a thing that goes. Again, it's just a single order. So it should also go at the same 20 dB, right? Does that make sense to everybody? If you don't, please ask. If it doesn't, please ask. Okay, does that look the same slope? That looks the but move everything. Yeah, the moving was just because I wanted. Oh, no. Okay. Yeah, that's okay. Even the previous one was okay. Okay. So basically, no? Okay. Let me remove this. Then remove the part. Omega 0 will be filtered out. Now, what is the of that filter? That's going to be again some R and a C, right? So the best it can do is 20 dB. It can't do anything better. So what's going to happen is equal to 0. First of all, the way I've plotted it, yeah, I should. This is not omega 0. That center is not omega 0 because this is a log scale, right? So yeah, tell me about this. How people didn't get this? Let me just move it so I have some space. Yeah. So the question I'm asking is, if I put this capacitor, this C1, and this C2, the moment the analysis we have done so far is, it includes CGD, but then C1, C2 are considered to be short, right? These are considered to be circuits. So the moment you include this one and 2, right, that is going to act as a filter. It's going to act as a high pass filter, right? That's how you design the C1 and C2. Let's go back in your notes also about 3-4 classes ago, right? Over here, right? How did you design this C1? You designed this C1 so that the basic idea was you included the C1, you worked out what's the ratio of this VGS to VS, right? You got this expression. There was this 1 by j omega C1. Now you wanted this to like the situation where you didn't have the capacitor, correct? So you find that will happen if this quantity is much greater than 1, and so you got a condition for C1, correct? So the moment you put this there, what is this response behaving as? It's behaving as this j omega by omega 1 divided by 1 plus j omega by omega 1. This omega 1 is not the omega 1 that we have been talking. It's not the frequency corresponding to the pole. Okay, it is this frequency corresponding to this RS and C1, right? And so we had plotted this also. You see this here, right? You have the plot. It's a high pass response. And now this corner frequency will come much lower than the than the dominant pole of our system. It is not an amplifier. Right? Do we get that now? Rajat? Then ask. How am I supposed to get if you don't ask? What's the problem? Forget about the shifting. Shifting was because I draw it correctly. Don't worry about the shifting. Okay. There's no shifting. Shifting is not the issue. But do you appreciate the fact that the analysis did not include the AC coupling capacitors or DC decoupling capacitors? So in the absence of including the effect of those capacitors, we just got low pass response dominated by the dominant pole. Now I am saying that to complete story, we should also appreciate that at lower frequency there is actually a high pass response because of the AC coupling capacitors, and that we had seen many classes ago, right? So we are not going to do the analysis including that, but you should keep that in mind. Is that clearer to people? Think about that. Okay. This high pass response has to be attached to the pass response that we are seeing. So I am going to attach here. Basically, when I moved it was, this is 20 dB per decade, right? This red line. The blue line also is 20 dB per decade. And I did this frequency to look like omega equal to 0. That's all. But this is a log, so this actually will not be 0. It will be, right? You can never plot 0 on a log scale, right? So this is some very small frequency, so 0.000, say 1. Okay. It's close to 0 but not 0. Right? So the better thing is not to worry about this, okay, and just say that right. So you will have a response like that. Your DC is somewhere this side. You get the point, right? You cannot plot 0 frequency on a log axis. The horizontal axis is the log axis. Okay. Right? So how do you actually show that? Okay. I don't know how one can show it in a clear. It will be at minus infinity, correct? Right? 0. So don't plot anything here. Okay. So maybe what I can to be clear, we should be clear because otherwise we are not engineers. So I can plot this and I mark this frequency, right? I can mark this frequency as, what's the name of this frequency? I call that the omega corresponding decoupling capacitors, the decoupling. What is the value of that? If this was R and C1, roughly what is that? That is by RSC1. Oh, wait. This is dangerous because what was omega 1? Omega 1 also had RS. Now that RS is a different RS corresponding to this. That was the effective RS of RA parallel RB plus the source resistance, right? We had called that as RS prime. But then I dropped the prime. So let me just not worry about this here. Okay. I'll remove. Right? Notional issue there, but the idea, right? What happens is that you have DC decoupling at low frequency and you have the dominant pole at high frequency, and effectively determines what your bandwidth is. But you will choose DC decoupling frequency to be very, very, very close to 0. So for all practical purposes, it will look like just having a flat response there and then a fall. Okay, all right. So what are the other things that we were looking at? Now let's go back here. I want to complete this, which is the phase response for the common source amplifier. Any hints as to what will happen? What is the phase going to be at close to 0? It will be same. Okay, at omega being infinity, what will be the case? Think carefully. Think carefully. How many of you say 0? Pi by 2 minus pi by 2. Why minus pi by 2?
Because again, it's pi by 2 by decade fall.
What is the response? So, this is subtlety which I wanted to point to you. When we were plotting the magnitude response, correct? You started off here, you said there is, look only at the red line. So, you said that there is pole corresponding to omega 1. So, that gives you minus 20 dB decade. Then, after omega 2, you have two poles in the system, correct? Both are active. So, you will have minus 40 dB decade. After the 0 frequency omega z, you have 1 0 which will compensate for one pole. So, it will go back to minus 20. That is for the magnitude. But for the phase, do you think the 0 will compensate the phase due to the pole? So it depends on where the 0 is. That's why we had considered situation where I was considering a right half plane 0. A right plane 0 uses a phase lag of pi by 2 from the low frequency, from the frequency below the corner frequency to after the corner frequency. Correct? So, on the other hand, if you have a left half plane 0, what will happen? Have a phase lead, right? What would a left half plane 0 look like? So, this is the right half plane 0. Can you tell me the same expression? Can you tell general form of a left half plane 0? So, I will just call this as an idea over here. General form of a left plane 0. That look like, what would that h of j look like? Sorry? So in simpler forms it will be some scale factor into 1 plus j omega by omega z. So the difference between this and this is the fact that here there is a minus sign. Correct? This thing is going to have this will have a pole on the left half plane. Sorry, this will have a 0 on the left half plane, right? Because in the corresponding h of s, what would h of s look like? 1 plus s omega z, right? So the pole is at, 0. I'll call that as sz. And what is that at? Minus omega z. Correct? So this is left half plane 0. Right? So you have a left plane 0 at omega equal to 0, your the phase lag, the phase would be 0, right? At omega being 0, it will just be the 1, so it will be 0. And at omega being infinity, pi by 2, right? So you will have a thing which is, so if I plot it over here, just for fun, right? If I have omega 0, if I take the same value of omega z, the left half 0, you will have something like, will you have, no. This is the problem with, where will he? They can tell me. On the same plot, I want to add this. So where will it look? So it will start from 0, right? It will start from 0 and what will it be at frequency? By 4, right? So that will be the situation for this left plane 0. Correct? So the left half plane 0 can cancel a pole which is right half plane pole. Sorry. So a left half plane 0 will cancel a left half plane pole. Right? What are these? Where are our poles? Our poles are left half plane poles, right? Where did we write that? Somewhere we wrote it. Okay, over here. And where did we work? Both the poles are left plane poles. They are all negative, right? The poles are negative. So if you have a left half plane pole and a left half plane 0, they have a tendency to fight with each other both in the magnitude and in the phase. On the other hand, if you have a left half pole and a right half plane like we have here, right, then in the magnitude response the pole has can fight with the in the magnitude response can fight with the pole, but in the phase response it may assist the pole. That is why, as Ishita pointed out, the phase in this system at omega being infinity will be minus pi by 2, because once you cross this omega z, basically that omega z, since this omega z is a right half plane 0, it is going to go phase lag of pi by 2. Correct? So that way here. So that would be of minus pi. Okay. So now you complete this. How will it look? So tell me at omega what should it become? It should become 3 pi 4. Correct? Then from this region all the way till omega 2, it should be in pi by 2. So all the way from here to till where? Yeah, so at omega 2 this should become pi by 4, right? So going to remain all the way, say up to there, somewhere up to here. Correct? And then at omega z it should come minus pi by 4, and at much higher frequencies it become minus pi by 2. Now just join all that together. Okay, these you should be very comfortable drawing. So go and spend some time, think about it. Now that you know to plot on Python, just consider some sort of function, plot exactly on Python, see what's happening. Right? How will it look from here to here? Some function. So am I correct? So this is pi by 2 up to here. It has crossed this. Okay, so let me say that, yeah, some function that, no, it should become actually 0 for some a, right, like that. And then okay, what is this red line? The red line is the phase response including the GD. Okay, so I see lot of blank faces here. Go and practice this. You know I have a good liking for Bode plots, so I'll keep shooting you with Bode plots. It's one of the most important things in engineering. You will see later that once we the topic that we're doing right, that's going to start today. Next topic after that is going to look at stability, and this is something you will course. You will again look at stability in control systems. Basically, all of you have experienced this when you were making the in the digital circuits lab, right? You came across one situation where if it didn't do things will start oscillating, right? Why? Because it was not a stable system. You started getting output at some frequency, right? So these kind of things have a tendency to become unstable, and in order to understand things become unstable, you need to be able to draw the Bode plot, both the magnitude and the phase. Okay, so we will see this. Let not confuse you now, but it's very important really to know when the gain becomes 1, what is the phase. So if at gain is 1, the phase difference becomes 180 degrees, effectively you have a system where something has got flipped. Right? So there is a thing regarding stability and how that plays into all of this. That's why I am saying the point that you should know about poles and zeros and how these things look. You will do it again in detail in your control systems class, but before that I think it's important that you know this. Okay, so go and practice this. Alright, now questions? Anurag, questions? Okay, now I had goofed up a little bit in these approximations, so let me just clarify that and then move ahead. Okay, that is, what were we doing? Where were we? Page up. Yeah, we took this, right, and then I goofed up a little bit, so let me just clean that up. So I'm we started off and we were trying to remove these various things to clean this up first. Okay, anyway, the moth eaten, but I think it's still alright. Right, you had this experiment and then we were trying to simplify this. So the first thing we said was that CG is much greater than CGD and CDB. Okay, there is no confusion in that. That is clear. So what does that allow you to do? That allows you to drop this CGD with respect to this CGS and this, what else? That's all, right? It allows you to drop the CGD with respect to this with respect to CGS. I forgot there was a GL, there should be a there's a GSL. Okay. Okay. The next approximation which we were doing, which I somehow I thought that was the right way to do it, but we got caught. Right? I claimed that you can GS much greater than GL. Right? Ordinarily your R is much less than R. Okay. So now I am going to my words. I am going to say that for this approximation, let us not do this. Okay. See, we are trying to get some intuition without going through the full calculation of finding out the roots of that equation. So for that, sometimes we can make some, even though this RS less than RL is a good approximation, if we make that, it's not going to simplify our expression. So we'll look in a slightly different regime where this is not the case, but it allows us to simplify things. Okay. So let me assume that my RS approximate the same order L. Okay, just for now. Now, what was the third thing? The third thing we had not explicitly mentioned, but is obvious because an amplifier. Can you say anything about GM by GL? Prakhar, GM by GL, is it small, large? It's going to be large, right? That's the gain of your amplifier. If that is not large, you can go home. There is no point doing all of this. So this by GL is going to be much greater than 1. Okay, so that's another thing so now let's take this and simplify it in a slightly different way. So get back what we had written, but it's cleaner. Okay, so I'm only going to look at this term, the S term, right? Only going to look at this term, right? So how should we proceed? So this, I can write that as S, right? Divided by what I had said earlier also. Okay, let me keep S by outside. I'm going to take GL inside. Okay, what are the terms that I will have? CS, the GL and this GL will go, correct? Plus S by GL CDB. Okay, let us not write it like that, because in all of this approximation, you write it also is helpful. So let GS by G plus G by GL CGD, right? No confusion. And what's the last term that I have?
CDB.
I'll again that will be GS by L times CD. Now you can use this approximation 3. Can you use approximation 3 and me what I can? I can kill this GS by GL with respect to this GM by GL, right? Because GS and GL are approximately same, right? Even if they are not, even if I say GS is, if I say RS, I say 1 order of magnitude more than RS, your GM by GL is going to be much larger because this is an ampere, right? So kill this one is valid. So I'll cut and I'll put that as 3 because of reason. This is because of reason 1, right? It's also because reason 1. All right, then what more do you kill? I want to kill this term. I want to kill this CDB term. How do you kill the CDB term? Or do you justify that the CDB term, killing it is okay? Yes, good. So if I compare this CGS and this T, right? CGS is greater than CDB. I'm saying GS by GL is approximately 1. That means I can kill that. So that is because of which, again, this is because of 3 and so what finally to the term? Because of sorry. Okay, so this term becomes effectively S by GS times CGS GM by GL times CG, which is what you wanted, right? You can do it more accurately and you will get some corrections. But this is enough for us to see the dominant frequency, the dominant pole coming from Miller's effect. That was the take home of all that stuff. Okay, so when we do analysis of the amplifier topologies, we won't do it in so much detail. I'll just look at the various resistors and capacitors, and then just by hand I will draw the Bode plot. Okay, so you should be familiar with all of this. Okay, so just to finish this closing remarks, then jumping a little bit. So the general function is second order, right? It has right half plane 0, is that right? Right half plane 0, 1. It has 2 half plane poles, correct? And the low frequency gain, so I'll call that as the gain at low frequency is, what's the low frequency gain? GML, right? These things, even if I take you from your midnights, you should be able to, right? Electrical engineer, you should do this. And what happens to the frequency response? Otherwise, roughly as A low frequency divided 1 plus A omega by omega 1, where omega is approximately 1 by S into P GS plus this low frequency in itself. GM by GL is frequency gain times what? PGD, right? And this is also bandwidth. There's an interesting thing which you will see later. I'll just leave with that thought. Calculate the product of the gain, okay, this A and the bandwidth. Just calculate quickly. I'm asking you to find the product of gain with assume it's the low frequency gain, which is want the amplifier to work. What will that be? Right? So if I call it as, so what will that be? It will be the A, call that A0 for A low frequency, divided by 1 plus J omega by 1 into omega 1. Omega 1 is your is that right? Right. And now this omega 1 itself is this whole thing. So can you simplify this? Just put in the low frequency at the bottom also and just surge it a little bit. Okay, let's not take this. This will be a little more complicated. Let me only take this. Just find out this product. What is this product? That will be, it is nothing but 0 divided by, right, 0 into This omega 1 is nothing but RSCGS plus A0 RCGD. Okay, and A0 very high. What can you write about this? In the limit of A0 being greater than 1, this is going to be 1 upon RSCGD. So thing into bandwidth is called gain bandwidth product, and it's a useful metric. Okay, we'll see that again, but just keep it in mind. What this is effectively telling you is that I have a trade-off. I can either have large bandwidth or I can have large gain. If I increase my gain at low frequency, if I increase it a lot, then my bandwidth is going to get killed. If I keep my low frequency gain low, then I am going to higher bandwidth. Okay, so that's a trade-off, very important, right? So this is essentially the take home that I want for the common source amplifier. You will see this gain bandwidth product for most amplifiers. When you do op amps also you will see. Okay, and so it's an important thing that you should keep in mind. Alright, okay, any questions on this? Okay, very good. So that brings us to the end of source amplifier, the common source amplifier, which we assume to be, we started off with, just quickly to recap, it's about 15 days of work, 20 days of work. Started off with how to analyze an incremental circuit, right? Then we looked at the bias point circuit. We wanted a certain kind of bias point circuit and a full circuit, right? Then we found that can do some kind of voltage divider. There was a problem with that voltage divider, so we said we want to get everything from a supply, and we did a few changes. Then we introduced this decoupling capacitor, but the motivation was by assuming it that behaves like a battery. Okay, that's an interesting of analysis. Okay, then we had this circuit in mind. We did a lot of the analysis, looked at its gain, right? Looked at its swing limits. Then looked at what is the maximum gain this will give. That was a function of what is the output impedance of the MOSFET itself, right? Then we did various AC coupling capacitors, and then we looked at the input and output impedance. We didn't work it out here, but you have done in your quiz, so you know that, right? So can you tell me, is the input impedance high or low, this thing? Low? High. It's a high input impedance. The limit of RA plus RB, RA parallel RB being infinity, right? Being very large, you will have a good, right? So your input impedance is good, is high, which is what you want. And your output impedance is a function of RD, is essentially R parallel RTS parallel RL, right? You can't directly say whether it is low or not, because your gain is a function of all of these things again, right? Your gain GM times RD this parallel RL. So if you make this low, then your gain will go low, but you will have low output impedance. So there's a trade-off there. So we will look at other topologies where you can reach some of these trade-offs. Okay. So any amplifier topology, you have to remember these things. What is its gain? Is it high, low? Is there any? What is its input impedance? Is it high, low? What's its output impedance? High, low? How is its frequency response? And what are its swing limits? Okay, that's what you should know for all the topologies that we will be doing. We will do 6 topologies. The common source amplifier with MOSFETs. Very similar is the common emitter amplifier with a BJT. Okay, that I can just do in like 10 minutes. Then you will have a common drain amplifier, which is similar to the common collector amplifier. You will have a common gate amplifier, which is similar to the common base amplifier. Your op amp, it will have many amplifiers cascaded together. So the goal of this course is to teach you how the internals of an op amp will appear. And you will see all of the stability we talked about, all of those things will appear. Okay, we need to go much faster.